So throughout this unit, I want you to keep in mind that all of the situations and scenarios are going to be based around constant acceleration. The acceleration will stay the same throughout each segment of a journey. So let's revisit some of the assumptions that we had in our last unit. We came across three terms which were vector measurements. We looked at displacement, velocity, and acceleration. Displacement is a vector. It can take positive and negative values. Velocity is a vector. It can take positive and negative values. Acceleration is a vector. It can take positive and negative values. And those positives and negatives are going to be massively important for us. We're not only interested in the magnitude, but also the direction. Displacement is the distance in a straight line between where an object currently is and its starting place. So it may have done a massive journey and then come back to where it started. It would have a displacement of 0, the distance from its starting point and its current position. So here the red particle has travelled on a wild winding journey from A to B. If we wanted to know the distance travelled, I'll be following this dotted line path. But the displacement is simply the distance from its starting position, point A, to its current position, point B. Regardless how far it travelled in between, just the measurement between those 2 points. Velocity is the rate of change of the displacement. How quickly is the displacement changing? Here we have 2 particles, A and B. They're both going to cover the same distance. They're both going to have the same displacement, but since one is going faster than the other, or one is completing the journey in a lower time than the other, it will have a larger velocity. So we see that B is completing that journey so much faster than A. It will have a higher velocity. In general, we can say that the velocity is going to be the change in S, the displacement, over the change in T, the time. I'm sure you've seen this delta notation, so it's a small change in S over a small change in T. And an example of the unit to use when we're working with velocity, it's a compound measure, is going to be meters per second. And moving on to acceleration, acceleration is the rate of change of the velocity. So we might have objects that all start with the same velocity and they might all increase their velocity, but how quickly is that increase happening? So here we have 3 objects, 3 vehicles that are on a journey, starting with different velocities, and each of their velocities are changing. If you notice, the blue vehicle, its velocity starts lower than the red one, and then it increases beyond the red's velocity. The green one also starts slower than the red one, and its velocity is increasing, but not as fast as the blue one. Acceleration is a measure of how quickly an object gets quicker. In general, acceleration is the change in velocity over the change in time. A standard unit that we can use here is going to be meters per second squared. Okay, so the velocity unit per second, meters per second squared. Okay, so let's actually look at all of this on a displacement time graph. So there are different things that are happening at different parts of this journey. We want to make sure that we can interpret what is actually happening at each individual part of the journey. So the red part, part A, we can see that the displacement has increased. It's gone from 0 to 30, and it's taken 2 hours to do that. We can find the velocity here. Velocity is the change in displacement divided by the change in time. So 30 divided by 2 would give us our velocity in kilometers per hour. Part B of the journey. Displacement has not changed. It was 30 at the beginning of part B, and it was 30 at the end of part B. There's been no movement. We can consider this object to have been stationary for this 1 hour interval. Part C. There is a positive change in the displacement. It's gone from being 30 kilometers away from the starting point to 60 kilometers away from the starting point. So that's a 30-kilometer displacement, and it's happened in half an hour. Previously, in part A, we had the same change in displacement, but it took 3 hours to happen. This has only taken half an hour. It's happened a lot quicker. The velocity in part C is going to be larger than the velocity in part A. We can see this graphically from having a steeper line. In part D, the displacement has changed, but this is actually a negative change. It's gone from 60 initially to 0 at the end of part D of this journey. So we have negative displacement, and this happens over an hour and a half. We could calculate the velocity by using negative 60 over 1.5 hours. So negative 60 divided by 1.5. And I'm sure that will get you negative 40 kilometers per hour. Okay, and I'll just recap that all on the screen for you. Be really careful here that you do pick up a negative velocity when appropriate. The negative velocity is when the object was moving closer to its start point. Okay, so let's have a look at a couple of journeys and see if we can tell what's going on in each stage. So here we have two separate journeys, but in both of them we can see that our protagonist, our character is going to be Tom. We can see that Tom has left his house, he stays stationary for some time, and then he heads back to his house. The difference in these two is that in the first one, he's leaving his house at a high speed and returning at a slower speed. And in the second one, he's leaving his house at a low speed and returning at a higher speed. So let's see which scenarios might fit that. So in the first one, Tom ran from his house to the bus stop, waited at the bus stop, realized he was way too late for the bus, and he walked home. So the high speed was the running, and the lower speed was the walking home. On the right hand side, he walked to the store at the end of the street, he bought a newspaper, and then he ran all the way back. Okay, so there's some subtle differences in these diagrams. Let's have a look at a few more. So in each of these journeys, there's multiple changes of velocity. What they have in common is that the displacement, the overall journey, is moving away from home. Just have a look at these and which scenarios might fit them best. Right, so you're probably best off pausing at this moment, try and figure out which scenario fits each of these situations. And here's what we should be looking for. Okay, and just a few more to look at. We can see that two of these, we've actually got curves to the diagrams, which means that we did not have constant velocity for these portions of the journey. The velocity was changing over time. Okay, and let's just see where they fit. Okay, so I just want to show you a displacement time graph that just has a little bit more going on, so it's a bit more of a complex version, but we're going to break down what's happening in each of these sections. So I've color coded each of the different parts of the journey just for easy reference as we make our way through. So if we wanted to talk about the initial and final position of this displacement time graph, the initial position is 0 meters away from where I'm measuring. Its final position, the very end of the journey, is 100 meters away in the positive direction. This means that the total displacement is 100 meters. Regardless of the fact that we can see there's quite a lot happening in the journey, we're only interested in the start point and its current position. So the total displacement is 100 meters. If we want to calculate the total distance traveled, I will be calculating and thinking about the distance traveled for each of these individual segments. So the first blue section, we've traveled 100 meters in the positive direction. The purple section, we haven't actually traveled at all, so I'm not going to consider that. The green section is also 100, and the blue section here is also 100. all three of them, the displacement has been 100 in the positive direction, but each line looks very different, has a different gradient because of the time it took to cover that distance. The purple section, we've turned around and we've walked back, or we've moved back in the direction we came from, 450 meters. The green section is a further 100, and finally the blue section is 350 meters in the positive direction again. We just want to add all of these together, and that's our total distance, 1,200. How about the speed for each part of the journey? So now that we know the distances, we're also going to consider how long it took to cover each of those distances. So the first blue section was 100 meters, and it took 50 seconds. 100 over 50 gives us 2 meters per second. The purple part of the journey, we didn't cover anything at all, so there's no speed to calculate. In the green part of the journey here, it was also 100 meters, but it only took 25 seconds. So the speed is larger, it was faster, it was 4 meters per second. This blue section, we can tell from the gradient of the line that the speed is going to be lower. It took 200 seconds. The speed is 0.5 meters per second. Okay, this purple section, so this is the stage where we start to come back on ourselves and go towards the starting position. We'll talk more about that in a minute. The distance travelled is 450 meters, and the time it took is 50 seconds. So 450 divided by 50, 9 meters per second. The green part of the journey, we travelled 100 meters, it took 75 seconds. 100 over 75, 4 over 3, or 1.33 meters per second. And finally, the last blue part of the journey, we travelled 350 meters, and it took us 25 seconds. 14 meters per second. Next, we're asked for the velocity of each part of the journey. This is going to be very similar to the calculation for speed, except we're going to need to take into consideration the direction we're moving. Are we moving away from the starting point, or are we moving towards the starting point? Are we moving in the positive direction and displacement is increasing, or are we moving in the negative direction and displacement is reducing? There are two parts of this journey where we're moving in the negative direction. So it's this purple part and this green part. For each of them, the calculation that we use is going to need to have negative displacement. So rather than the distance, we're using the displacement. So this initial one is negative 450 over 50, negative 9 meters per second. The second one, negative 100 over 75, negative 1.33 meters per second. Okay, and then just to finish off with the average speed and the average velocity. With speed, the numerator needs to be the total distance travelled, while the average velocity is just the total displacement. So in this instance, we're going to have 1,200 over 450, 2.67 meters per second. But when it comes to velocity, we're only using 100 over 450. That's 0.22 meters per second. Okay, so here I've tried to demonstrate the differences between speed and velocity, the difference between distance and displacement, the difference between a scalar measurement and a vector measurement. And just to finish up, a reminder of what we're looking for in a displacement time graph. Horizontal lines are showing that an object is stationary. Straight diagonals are showing that an object is moving with constant velocity. And if you come across any curved parts to the diagram, it shows that the object is accelerating. So as usual, you can move on now to the pre-quiz and some practice questions.